Welcome to another video. So this is a previous year KTU problem. This is a theory problem. This is from module 5 of MoS, and in module 5 this is from the column section. Okay. Now this the question is define slenderness ratio and kern of a circular section. Okay. Generally this kern is always asked. Kern of a circular section is asked sometimes. Sometimes it is not rectangular section. These two are very common. Instead of kern, sometimes they use core. They will use the term core also. Okay, core also is being used. Generally, on mechanical papers, we have seen use this core. Sometimes they are also called as kernel. Okay, so all these are means one and the same. What is the meaning of this? We will discuss in this. So first, we will see what is slenderness ratio. Slenderness ratio. So slenderness ratio is a ratio. It is a ratio of it's ratio of effective length to radius of gyration of column. Or you can say effective length to least radius of gyration. Least radius of gyration. Sometimes some column will have multiple radius of gyration. Some rectangles have 2 radius of gyrations. Circle have only 1 radius of gyration. So when it is rectangle, you have to take the lower value. Okay. So basically, mathematically, if you write that, that is nothing but effective length upon k. This is slenderness ratio. This is what is called slenderness ratio. Sometimes it is denoted by lambda, or you just write slenderness ratio. So effective length, capital LE or small LE, both are any of the convention you can use. Effective length, slenderness ratio, effective length depends upon the length of the column and the support conditions. This we have discussed in a previous video how to find slenderness ratio. Now K is radius of gyration. How do you find K? K is given by under root of I by A. Okay. So or we can say I equal to AK square. AK square. So either of this you can use. It is one and the same. So this is how you find radius of gyration. So in rectangular section, you can get 2 radius of gyration, 2i. So with respect to this, we can have. So let's say I'll call this as xx. I'll call this as yy. You can have ixx or iyy. So in that, the least value you have to take, that is ixx will be lesser than iyy. So ixx you have to take to find the slenderness ratio. Okay. So that it is very important. That is the meaning of this least that I have added later. So in the meaning of that is when you consider this, when you find the radius of gyration, you have to use the I, which is least of the section. Okay, that's very, very important point. Now, so this is slenderness ratio. Now slenderness ratio, if you see what is the unit of slenderness ratio, it doesn't have units. Slenderness ratio is units. So these are the important points that you have to come right. So one is the definition. How is it defined? Then what is K? What is LE? LE is effective length. So you can also write LE depends upon length of the column and boundary conditions. Okay. So once you write this much, I think this is more than enough. So this is about slenderness ratio. Now what is kern of a section? Now kern, it's very useful quantity. So basically, they are asking what is the kern of a circular section. So basically, they are just asking you what is the value of kern of a circular section. So if this is a circular section of D, there is a small area inside the circular section that is of diameter D by 4, which is known as the kern of a circular section, or core of a circular section, or kernel of a circular section. Okay, kernel of a circular section. The meaning of this is kern is nothing but area or region in a column wherein wherein which when we place axial load, the entire column will be under compressive stress. Okay, sorry for the bad handwriting. So basically it means that there is a small region inside the column. So for a circular section, the core is d by 4. You have to remember this. So inside this with d by 4, we have a region here. Okay, the diameter of this region is d by 4. So when you put load inside that region, okay, so what do you mean by load inside this region? So if the column is like this, something like this, it is going like this. So let's say, give me a moment. So let's say the column is something like this. Okay. Now if you put, so this is a Kern. So if you put load inside this Kern, the entire section will be in compression. If you keep load outside the Kern region, what will happen? So somewhere here or here, anywhere outside the Kern region, there will be some tensile stress that is coming in the column. Now, what is the reason for this? So basically, when the load is at the center, there is only axial force. When the load is at some distance from the center, there is some eccentricity. Because of eccentricity, there is a moment. Okay. So when the load is at center, we have total compressive load in the column. So if I call this as P, it is P by A compression. It is at center. Now, if load is at some distance from the center, so let's say if this is center of the column, if it is at some distance, normally denoted by E, then it is nothing but it is same as the same column with some moment. So the value of moment will be P into E. Okay, when there is a moment, basically what happens, there is a moment in the column. So this region will be in compression, this region will be in tension. So it will look something like this. So this region will be in compression, this region will be in tension. Okay, so this is the distribution of bending stress. Because of movement, bending moment, bending stress will develop. Bending stress is not uniform like axial stress, it will vary. So one portion you will have compression, one portion you can have tension. So this you can imagine also when you try to bend this. So let's say the column is like this. When you apply load, it will try to bend like this. It will bend like this. So this portion we have tension, this portion will have compression. So that is denoted here. This is tension, this is compression. Okay. So up to certain value of this eccentricity, there will be net compression. So you have to when there is axial force, you have to add these two. So they basically PE is that there will be also an axial load P. So P and PE. So this is the net effect of this eccentric loading. So because of eccentric loading, there will be the P value here, and there is the moment which is P into E, which is coming on the column. Because of P, the distribution will be like this. Because of moment, the distribution will be like this. Okay. Now, up to certain point, whatever tension is coming, it can be contained in this compression. After some time, what happens? There will be tension developing in the column. Okay. So, all in all, what you have to answer for this question is, Kern of a circular section is the inner region of the column with a diameter d by 4, wherein which, if you keep a load, the entire column will be under compressive stress. The moment we place a load beyond the Kern, any other point beyond the Kern, it is 100% sure that the section there will be some tension in the column. Okay. So this is the meaning of Kern of a circular section. So I hope this is clear. We will solve another problem in the next video.